Building Information Modeling, or BIM, promises a nearly perfect digital twin of a building. In this ideal scenario, every beam, wire, and pipe is perfectly coordinated before a single shovel hits the dirt. The reality of modern construction involves dozens of highly specialized teams. Architects, structural engineers, and mechanical contractors all work in relative isolation, even as they attempt to design the exact same physical project simultaneously. As this animated diagram illustrates, the system breaks down when those isolated teams use different software platforms, operate on varying timelines, and model at different levels of detail. That shared model quickly fractures into thousands of data conflicts. Attempting to build a shared digital model without a standardized framework for collaboration leads to digital mismatches that inevitably turn into physical delays on the construction site. Just as a physical structure requires a set of blueprints, the digital version of a project requires a blueprint for how information is shared. This is the BIM Execution Plan, or BEP. It is the employer-approved master playbook that establishes the rules for coordination, the roles of each team, and the technical infrastructure the entire project will rely on. By locking in these parameters early, the BEP transforms BIM from a fragmented software exercise into a systemic engineering tool. To manage data flow, the BEP establishes a human hierarchy, led by the BIM manager. This person acts as the primary digital orchestrator, facilitating coordination meetings and holding the final authority on how the execution plan is applied. Below the manager are the model authors. The BEP explicitly identifies these authors because they carry responsibility for developing the exact geometric content and data of specific elements, like a structural wall or a ventilation shaft. Authors are distinct from model users. Users do not create the geometry. Instead, they inherit the author's approved data to perform downstream tasks, such as calculating construction costs or building out delivery schedules. Strictly defining these roles prevents the confusion that arises from overlapping edits, ensuring accountability for every piece of data in the project ecosystem. Beyond the people, the BEP dictates technical requirements. It maps out exactly what data must be delivered at specific gateways, such as conceptual design, then detailed design, and the final construction phase. We can see this progression in the level of detail, or LOD. A column might start as a simple gray massing box in early design. By the construction phase, it has evolved to include precise exterior dimensions, internal rebar, and specific material data. The BEP mandates exactly which LOD is required at each milestone. To ensure that a highly detailed column can be read across different software programs, the BEP enforces specific naming conventions and standardized metadata tags. These strict technical standards ensure that a digital wall or pipe is universally understood by every machine and contractor working on the project. The BEP functions as a contractually binding document, governed by a specific legal framework known as the BIM Particular Conditions. These conditions legally define and protect the intellectual property of the individual model authors. They also explicitly limit liability. If a model user decides to order structural steel based on an early, low-detail schematic, the legal framework protects the original designer from the consequences of that premature reliance. To settle potential disputes, the contract formally identifies a final design model. If there is ever an inconsistency between various 3D models or printed 2D drawings, the final design model legally prevails. Without this framework, firms would likely hoard their data to avoid legal risk. The BEP provides the legal safety net required for competing firms to openly share their intellectual property. All of this planning reaches its peak during construction. This is the milestone where individual architectural, structural, and mechanical models merge into a single federated construction model. This diagram shows the process of virtual clash detection. The federated model scans for physical interferences, generating flashing red nodes where a mechanical air duct accidentally intersects a structural beam. Moving an air duct in a software program is a matter of coordination and logic. Discovering that same clash on an active job site means halting labor, ordering new materials, and tearing open finished architecture. The BEP's value lies in shifting the expensive trial and error process from the physical site into a digital space, where errors are identified long before they require concrete and steel. The usefulness of this data extends far beyond the day the building physically opens. The lifespan of the digital building continues right into the operations and maintenance phase. As illustrated in this animated timeline, the BEP dictates one final handoff. The entire linear construction history compresses into a single cube of data, the project information model, which is then converted into a circular asset information model, or AIM. Facility managers take ownership of this data-rich digital twin, using it to track maintenance schedules and locate physical components hidden behind walls for decades to come. The BIM Execution Plan acts as the invisible scaffolding of modern construction. You must fully engineer the digital collaboration before you can effectively build the physical reality.